In the last class we were discussing this vibration absorber. So let's continue this discussion. So this machine has a mass of 50 kg with two springs. This is 0.5 into 10 power 5 Newton per meter, and this is also 0.5 into 10 power 5 Newton per meter. X1 is the displacement. There's a forced frequency which is f0 sine omega t, which is 1200 sine 45 t. So omega is 45 radians per second. So for this we need to have an absorber which can absorb the vibration of this machine. So what is the given data is the mass of the absorber is given. Mass of the absorber is 5 kgs. So we need to determine the stiffness of the absorber that is to be used. So this is how much. So let's draw a vibration absorber. So this is consists of a spring and then a mass. So this is M2, that is mass of the absorber, which is 5 kg, and this is say K2, which is stiffness of the absorber. So we know that from the last discussion that omega is equal to root of K2 by M2. This is to be satisfied if A1 is to be 0, that is the vibration of the machine. If it is to be 0, then the forced frequency must be equal to the natural frequency of the absorber. So K2 is the stiffness of the absorber and M2 is the mass of the absorber. So from this, here omega is given as 45 radians per second. So 45 is equal to root of K2 divided by mass of the absorber is given 5 kg. So K2 will be equal to 1.01. If we calculate this, it will be 1.01 into 10 to the power 4 Newton per meter. So if we use a stiffness of 1.01 into 10 to the power 4 Newton per meter for the spring of the absorber, and mass of the absorber is 5 kg, then the vibration would be absorbed by this absorber if the force frequency is 45 radians per second. So this is actually a 2 degrees of freedom system because this is x2. So if we draw this, so this will be the first spring, and this will be the machine, and this would be the spring of the absorber, and then the mass of the absorber. So this is how much? This is 1 into 10 power 5 Newton per meter. So it is 0.5 plus 0.5 into 10 power 5 Newton per meter. So it is in parallel. So I have added these two. M1 is 50 kg. So this is 50 kg, and this is X1, and this is X2, and this is 5 kg. The stiffness of the spring is 1.01 into 10 to the power 4 Newton per meter. So there is also a forced frequency over here, so which is 1200 sine 45 t. Okay, so what we need to calculate is, we need to calculate the, since this is a 2 degrees of freedom system, we need to calculate the natural frequencies. So natural frequency of the first one and natural frequency of the second one for a 2 degrees of freedom system. So this is also 2 degrees of freedom system. So we need to calculate this. The procedure is, we have already discussed the procedure of how to calculate this. It is, you just have to draw the free body diagrams of this M1 and M2 and show the displacements, and you need not worry about this force frequency when you are calculating the natural frequency. So it is very similar to what we have done previously. So we have solved problems of 2 mass and 2 springs. So if you solve it, you need not worry about this 1200 sine 45t to calculate the natural frequencies of a 2 degrees of freedom system. When you do this, you actually get this to be equal to, first frequency would be 38.27 radians per second. I'm not going to solve this, but I'm just giving you the answer so you can practice this. You can try to calculate and see if you are getting the same, because we have already solved such numericals, so I'm not going to repeat this. So we have got the first natural frequency as 38.27 radians per second and the second natural frequency of 52.49 radians per second. So what does this mean? And we have omega as 45 radians per second as per the given problem. So where is the amplitude going to be larger? It's going to be larger at the natural frequencies when it matches with the force frequency. So instead of 45 radians per second, if the force frequency was 38.27 radians per second, then the whole system would vibrate with a large amplitude. If instead of 45 radians per second, if the force frequency was 52.49 radians per second, then also the this whole system would resonate, that is vibrate with a large amplitude. Only when the force frequency is 45 radians per second, the amplitude of the machine, so this is M1 is the machine, so the amplitude of vibration of the machine is going to be 0. So if we can represent this, so if this is A1 and this is say 38, this side is omega, that is force frequency, 38.27 radians per second. So this is in radians per second, and this is say 45. So this is 38.27 and this is 45 and this is 52.49 radians per second. What it means is the amplitude of vibration of this machine is going to be 0 only at 45 radians per second. So it's going to be 0 over here. Okay. So what is it? So how much is the amplitude going to be at 38.27 radians per second? Because this is the forced frequency and that is being equal to the first natural frequency of this 2 degrees of freedom system, the amplitude of vibration is going to be infinity. So it's going to be infinity over here, and it's also going to be infinity over this 52.49 radians per second. So what do we have here? So the amplitude of vibration is 0 only when the force frequency of the machine is 45 radians per second. If it is anything other than that, the amplitude is going to increase, and little closer to this is 38.27, and little after that is 52.49 radians per second. These two are the natural frequencies of the 2 degrees of freedom system, and when the forced frequency matches this natural frequency of the 2 degrees of freedom system, it is going to resonate, but only at 45 radians per second. It's going to be, the amplitude is going to be 0, because this absorber is going to absorb the vibrations of this machine at 45 radians per second. So what do we understand by this? We understand that the absorber, the vibration absorber, which is also called as the dynamic vibration absorber or the tuned mass damper, these are the different names by which it is called. It is called the dynamic vibration absorber or the tuned mass damper. So what it means is, it is tuned, this absorber is tuned for this particular frequency. So any deviation is going to increase the amplitude of vibration. So the application would be in situations where the forced frequency is not going to vary. So you're going to operate at that particular frequency for which the absorber is designed for. So only in such cases you will use the vibration absorber. If you are going to vary the forced frequency over a range, you cannot use the vibration absorber to absorb the vibrations of the machine. So this is what we need to understand. So it's a very narrow range. So little over this side you can go, little over this side you can go, but more than that, if you vary the forced frequency, you're going to increase the amplitude of the machine. It's not, the absorber is not going to absorb the vibration of the machine for a wide range of frequencies. So this is what we need to understand from the concepts of the vibration absorber. Thank you.